Okay, model cycling. Here the number of steps, here is unbalance force in Newton units, and here is AQ ratio. We can refresh. Oh, there is a problem here, and we don't have connection of this grid point with this beam nodes. Okay, we stop. Okay. Great region. Okay. Here you can see we have this grid point 78 in I and 28 in J. As you can see, structural element is this line, and but there is not any connection between grid points of zones, and this node of structural element, and just the attachment between this grid point and node of structural element is. So also maybe here, maybe we don't have connection between this GP, this grid point, with node of structural beam element. Just connection is between this grid point, this, and these nodes of structural element. Because installing the beam element in a long way, as you remember, we have used the long way for installing this beam element. Installing the beam element in a long way has caused the connection to not be established at the grid point, this grid point, and this grid point. The connection to not be established at the grid point include the interface and the beam. This grid point have interface and structural elements. And only one of the grid points, just these and this grid point is only one of the grid points at this point is connected to the beam element, and so we need to install this area separately from the beam element. Okay. As you can see, we don't have two grid points here, one this and one for this region, one for this region, two grid points. Okay, we delete the codes of structure element, rebuild, and we go to the structure tab, beam tab, and we remove the tick-up line and attach and install the structure element to the wall of tunnel with a mouse without long way. Okay, we drag here. Okay, we will have connection between the structural element beam with this grid point, this, And as you know, there are two grid points here and here. And with other drag, you will have attachment of grid point with node of structural element. Okay, good. Here and okay, good. It's okay. And execute and structural element property. Cross-sectional area is 0.1. Moment inertia is 8.333 E minus 5. 2D 3D equivalence is continuous in the direction for shotcrete. Mechanical Young modulus is 7.467 E9, and density is 2200 kilogram per cubic meter. Okay, execute and run. Okay, the model is cycling. Okay, we can refresh and check the plots, plots of displacement. Refresh. We have 2.5 centimeters settlement in the cone of tunnel in area of fault zone. 4 centimeters, 5 centimeters, and the value of equal ratio is high. Also, unbalanced force is high. Okay. We will have refresh automatically in 5 seconds, in each 5 seconds. Okay, 7 centimeters. It's not good, and we don't have stability of channel in shotcrete element. It is so strange because in the FLAC 9 we had a stability with 10 centimeters thickness shotcrete, and it's so to say strange. Okay, we stop the running and change the thickness of the shotcrete of element, beam structure element, and moment inertia. We set 35 centimeters for thickness, so we will have a 0.35 area, cross-sectional area, and this value for moment of inertia, and rebuild. As I told, it is strange because we had a stability in FLAC 9 with shotcrete, with 10 centimeter shotcrete. Also, another interesting thing is about capable. We had a stability in FLAC 8 with capable structural element, but in FLAC 9 we didn't have any stability with cable structural element. And for this subject, for these issues, we must study more and find the reason for this mismatch. Okay, equal ratio is low and we are reaching to 1 e minus 3. Okay, we had a equilibrium and good maximum settlement of tunnel crown is 1.7 centimeters. Okay, good. We create a clone with the name of steel arc. Okay, and delete the codes of beam elements. Rebuild again. Okay, and we want to create the steel arc with the linear structural element. As you remember, we had this image in the slide of PowerPoint, and I told we can simulate a steel arc with the linear element with the parameters of shape factor. We have different shape factors for different cross-sectional of linear element, rectangle cross-section, circle cross-section, and pipe cross-section, cylinder, and a steel arc cross-section with MPI profile. And shape factor for this cross-section is web area divided total area. Web area is this area, and we will calculate area of web and divide to total area of cross section. Okay, go to the structure tab, liner tab. Okay, okay, execute. Structure element property, shape factor will be shape factor 0.3, so and so on. Okay, and we select this option, height and width. Height is 120 millimeters. Okay, and width is 58 millimeters. Okay, a space, we can select a space 1 meter spacing in Z direction. And the Young modulus will be 210 gigapascal E9. And Poisson ratio will be 0.3. Density will be 7,850. Okay, execute. Okay. I want to change the spacing to 80 centimeter. Okay. Run. Okay. Model is cycling. Refresh plot. We have 2 centimeters settlement in this area. 3 centimeters minus 3 centimeters. 70,000 steps. 4.5 centimeters. Refresh plot. In the faulted zone, we have maximum settlement. 6 centimeters. Settlement. 7 centimeters. We have high value of settlement. 7 centimeters is high value for a settlement of tunnel and stability phase. 8 centimeters. Refresh plots. We have maximum settlement here. 9 centimeters. Refresh plots. 10 centimeters. But I want to continue the cycling because equal ratio is smaller. Okay, we have we have an equilibrium, and also we have a relative stability. But of course, this settlement 10 centimeter is a high value, 10 centimeter, but we have an equilibrium. Okay, save. Good. We have a stability in the still arc. We don't the stability with shotcrete 10 centimeters. We have a stability uh, with shotcrete 35 centimeters. Also, we have stability with cable bolts. Okay, we create another clone with the name still arc cable and shot. Okay, in this clone, we will have the combination of all structural elements, still arc with linear, cable bolt with cable structural element, shotcrete with beam structural element. Okay, let's go. We go to the cable bolt and edit and select all codes, copy, save again, and back to the stellar cable bolt stage save. Okay, select these codes and paste here. rebuild, edit. Okay, we have here capable structural element. We go to the beam tab and create shotcrete beam element. Okay. Oh, clear. Okay. This area and this area and this. Okay, execute. Save and shut section and copy these codes. Save back to the SLR cable shot section and paste here. Rebuild again. Okay. We have cable bolt and shotcrete. Shotcrete with beam element, cable bolt. So we must to add a steel arc with the liner element. Okay, structure liner tab. Here we can add and create liner element with two methods, with two options. One option is with interface. We can use interface and add a gap. Gap here is 10 centimeters because we have a 10 centimeter shotcrete. And so we can create with these options, for example, here, and add properties of interface. For this option, we have connection between, we have interface between liner element and grid points of zones. And we must to use this option when we want to delete the beam element in the future, in the next steps. But if we don't need to delete the beam element in the next steps, we can use these options and create a liner on the beam. Okay. Okay. We drag with mouse around of tunnel. Okay, good. We select bounded interface with normal stiffness equal for E9. Also shear stiffness for E9, cohesion 0, dilation 0. Friction angle of interface between steel arc and shotcrete will be 20 degrees. Tensile bond strength will be 1 E5. 100 kilopascal. Okay, execute. Okay, it's good. And now I want to run and solve. Structure. Okay, we didn't assign property of steel arc or liner element. Save. Go the steel arc save it and copy the property of linear element and paste here. Repeat and solve. Refresh. Check Y displacement. Right now we have 4.5 millimeters settlement in this region. Refresh. Oh, okay. Equal ratio is closing to the 1 p minus 3. The number of steps are 44,000, 45,000. Refresh plot. Chain check SYY stress, vertical total stress. Also, we can check plasticity indicator, cable element axial force, moment of linear element, the values of maximum value of moment in linear element is low value. Okay. Oh, but there is a problem here. We have an equilibrium and but we have a problem about the property of shotcrete. We must to change property of shotcrete to 10 centimeters. Okay, and okay, now rebuild again. Okay, okay, we have settlement 1.2 centimeters in this region again, and so you can see the increasing of settlement with 10 centimeters shotcrete in comparison 35 centimeters. In 35 centimeters shotcrete we had a 7.5 millimeter settlement, but now we have 1.2 centimeters. Okay. We are reaching to default value of equal ratio. That means 1 0.000 minus 3. The number of steps are 74,000, and you can see the values of ambulance code. Okay, we have a stability and we have an equilibrium here. Okay, say in this stage and in this say we have combination of cable ball, beams and liners for steel arc, cables for ball, beams for shotcrete. Okay, we can check the displacement in other SIV. In the steel arc, we have 10 centimeters settlement in this region. In the shot SIV and in the shot scenario, we have 1.7 centimeters settlement in this area, but of course with 35 centimeters thickness. In the cable wall, we have 3 centimeters settlement in this area. So we can conclude the smallest and the lower value for settlement of tower crow is in the scenario of steel arc, cable and shotcrete combinations. Okay. That means we have 1.2 centimeters settlement in the area, in the faulted zone area, and uplift of 3 millimeters in this region, in the region of faulted zone. Okay, nice. We will have another another session about an ATM tunnel and excavation scenario with the side drift methods in the next session. Okay, goodbye.